the third talk in the 2014-2015 SIG webinar series. Just as a reminder, presentations in the series are approximately 50 minutes in length, with questions and answers following during the remaining time. Today's webinar is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and presenter will have their microphones enabled. One of our speakers today is coming to us from France, so there's a very noticeable audio and video delay. So please be patient, as sometimes the audio and the video may not be in sync. Hence, we also encourage you to use the chat window to type in your questions or to communicate with others due to the delay. So today we have Professor Louise Kellogg and Dr. Pierre Arial. Louise is a professor at UC Davis and both the director of CIG and the Keck Caves. She has a range of interests and expertise spanning mantle convection, numerical methods, earthquake physics, and crustal deformation, immersive visualization, and the intersection of art, science, and technology. Pierre received his Ph.D. from the University of Nantes, France, on thermomechanical and fluid transports in subduction zones. Today, Louise will begin by sharing her thoughts on benchmarking in geodynamics, and then Peter will walk us through some of his work as a postdoctoral scholar at UC Davis in his talk, Influence of Numerical Discretization on Preferred Thermal Convection Pattern, 3D Spherical Shell. So Louise, we'll start with you.
Okay, well, thank you, Lorraine. I appreciate it, and thank you to everybody for coming to the webinar. It's always great to be able to interact with people who are all over the world. So this work was motivated, I'm just going to give a very brief introduction. This work was motivated really by one of the challenges that we have for solving governing equations of mantle convection, and also a challenge for a variety of computational problems, and that is how to best discretize the computational domain, in the case of the mantle, the spherical shell, so as to produce an efficient and an accurate solution. And so this is there are a variety of approaches to take that people take to this. And a few years ago, there was a CIG workshop held in Santa Fe that brought together geophysicists and computer scientists and also applied mathematicians, not specifically to address that problem, but to address the overall questions of what the frontiers are in modeling mantle and lithospheric dynamics. And that meeting, as often these meetings do, created some new synergies and introduced me to two mathematicians who were considering how to solve problems on a spherical shell. That's Natasha Flyer from the National Center for Atmospheric Research and Grady Wright from Boise State University. So the NCAR affiliation lets you know that they were interested in problems of on a spherical shell to look at atmospheric circulation and perhaps ocean circulation as well. And so they made us aware of a method called radial basis functions, which is a meshless method for discretizing a spherical shell, and they were using that to solve partial differential equations of a similar but slightly different sort than we are doing here. So we started working with them. We obtained some funding from the National Science Foundation's collaborations in mathematical geosciences, which brought together mathematicians and geoscientists to work together on methods. And we started looking at whether the RBF method would be suitable for solving mantle convection type problems. In the course of doing that, they built a solution to the mantle convection equations, and we started testing it, we used the well-established code CitcomS to do comparisons. And as we explored some of the solutions, we discovered that some of the classical solutions for convection in a spherical shell were not necessarily as stable as one might think they would be. So this led us to explore a little bit some of the physics of the origins and stability of convection patterns in 3D spherical shell, and I think that's what Pierre tell you about. And so as you listen to what Pierre talks about, one thing to keep in mind is the physics of this problem, and another thing to keep in mind is the implications of this sort of analysis of the stability of solutions for benchmarking, for testing codes as we go forward. And so I'm going to, Pierre has some very interesting results to talk to you about, and so I'm going to turn it over. Take it away, Pierre.
Yes, thank you, Louise. Thank you for this this introduction. So, good afternoon, everybody. I would like first to thank you, CIG, to the opportunity to present the result of this work. And so, I will briefly introduce the motivation of this work before to show you some results and some methods that we obtain for different test skills. And I will also, just before this, I will also introduce some new polynomial patterns of convection which have never been presented before in literature. So Louise already did a really good introduction of the purpose of this talk. So I just want to precise that 3D numerical simulations of thermal constants in spherical have become really standard for studying the dynamics of patterns formation and its stability under perturbation to various parameter value. So steady-state pattern formations have been predicted by nonlinear perturbation theory. So at the end of the 70s, and for example, the tetrahedral patterns or the cubic patterns, and so some of these structures have been numerically verified by several authors during the following decades. And so in particular, the tetrahedral patterns, the cubic patterns. So you can see on this side two examples of these convection patterns. I will just briefly describe what the color means here for the rest of the talk. So these two figures represent the for the temperature. So the result temperature means it is a variation of temperature in one point in the model with the average temperature at the same depth. So it means for the yellow idle surface, it means that it is a positive of result temperature. So it is in the mantle where the temperature is higher, the average temperature. So it means it's the location where the fluid is upwelling, is going upward, the metals, and the blue idle surface are the result temperature. Means it's the region temperature is lower than the average temperature, so it's a region where the fluid is going downward into the mantles, and the red sphere in the center is just the core. So so if the tetrahedral and cubic pattern are known now, the behavior of steady-state solution with higher order of symmetry has not been examined, and in particular the dodecahedral initial conditions. And further of this pattern is almost never been investigated, and only the predicted have been fully tested. So for me, the question arises is about the stability of this different patterns of convections, and if they are sensitive to different numericals or from numerical comparison. So I'm going to comparison between three different numerical codes. So the two finite-element code, CitcomS and aspect, and a pseudo-spectral code called RBF. And so first I'm going to show you results of two different case cases. So the first test will be the cubic or octagonal initial conditions, and in the second time I will show you the results for the dodecahedral initial conditions. So I will first briefly describe you the three different codes that we use for this comparison. So first, CitcomS, so it's a finite-element code, and CitcomS is using three linear bricks elements. One of the particularity of this code is divided in 12 vertical caps. And so each cap represents more or less like a cube, and these caps are divided by, for our simulations, is divided in 48 by 48 by 48 elements. So if you want to have more information for CitcomS, I will encourage you to join the website. So the second code is called RBF in this presentation. So RBF means radial basis functions. So it's a pseudo-spectral code, and it has developed Grady Wright and Natasha Flyer. And if you want to have more information about the mathematical background, you can go and see the GQ paper. So the real mesh in this code, the sphere is described with points, and we define Chebyshev points and Chebyshev polynomials in the radial directions, while for the directions we have they use so basically the resolution of the is resolution of the models will be given by the combination of the two nodes combination. And so the last code that we used is aspect. So we introduced this code in the comparison really late in the study. So we only performed few models with aspect, but aspect it's a new metal convection software which can improve or participate to this comparison. So it's a finite-element code, and it's based on new or modern library like DIL2 for finite element or Trinos for linear algebra. And another particular aspect that we try to use in this comparison is to use the adaptive mesh refinement. So on this figure you can see an example of the refinement that we obtain for model for size in the sphere. And so if you want to have more information aspect, you can visit one of these two websites. So to investigate the influence of polynomial formations in metal convections, in isoviscous metal convections. So one of the key parameters is to be the initial conditions. So in all of our models, we are going to impose first time a pure conductive temperature profile, which corresponds to the left part of the here on top. And the key point of this initial condition is going to be the amount of the additional perturbation is going to be added to this pure conductive profile. And so it's a TP here in the second part of the regions, and this initial perturbation is going to define the location of different anomalies, and is going to generate the patterns of convections. This perturbation is a combination of two harmonics, and so the YLM parameter is the normalized spherical harmonics of degree L, and same order. So yeah, I just want also to precise that the for all conditions, the geometry of the sphere is going to be corresponding to an aspect ratio of the Earth, and we also are using isoviscous in particular because the RBF couldn't model variable viscosity, and also we only models heated from below and cooled from above. No internal heating in any of these models. So I'm now going to show you and to present you the first test cases. So it's about the cubic initial conditions. So cubic initial given by this equation. So as the perturbation corresponds to a combination of two spherical harmonics of degree 4, and we introduce an distribution called delta here to destabilize initial symmetry. So basically, we have delta equal to 0. We have the classical cubic initial conditions corresponding to the first figure here on the top. And when we increase this value the impact on conditions is to decrease the amplitude of the four anomalies along the equator, and they are going to closely merge together. And when we have a value of delta, the initial condition corresponds to pure axis symmetric initial condition. So it's we only have the left part of the spherical harmonics. So it's only the y for 0 symmetry. So investigated the influence of this perturbation at various Rayleigh. So I'm going first to show you an example of the low Rayleigh number. So low Rayleigh number means lower than 10,000. And so this figure represents the evolution of the final pattern of convection, so the steady state pattern of convections as a function of the additional so the additional perturbation delta is decreasing from the left to the right. So we can see here that the result of the three different code, and so in the first time, so we can observe that we can convert state patterns for model even increase the perturbation up to 0.3 for CitcomS and RBF, and for 0.29 with aspect. So the value of this perturbation is really different between the three models are really small, and consider that they have a pretty good agreement for to localize the transition. So cubic steady state is destabilized. It's supposed to be destabilized to the end member of the initial condition. I mean, it's supposed to be an axisymmetric steady state. So for RBF and aspect, we observe that the very short these two parts. While for CitcomS, observe that there is something like a transition, and for only very small amount of perturbations, we can observe transition patterns. So I'm just going to show you a few animations to show you how this pattern evolve with time. So first, it's for the state. Okay. So you can see when the convection starts, so the plumes are really starting where the initial perturbation is located. So now I'm first going to show you the axisymmetric steady state. So in this case, you can see that the 4 points around the equator are not strong enough to stay separate, so they are going to merge together and finally converge to the axisymmetric pattern. And for the transition patterns with CitcomS, so these patterns is very similar to the axisymmetric evolutions. Just seems that 2 plumes are going to merge together without really complete to merge really along the sphere. So we didn't observe these transition patterns for RBF and aspect, and so we also never observed this kind of patterns for the code or of our situations. So it might be possible that this kind of transition pattern might be something like an artifact generated by the discretization method in CitcomS. So we can also see the variation or the influence of this additional perturbation on the transient evolution of some parameters. So here you have the evolution of average temperature as a function of time for RBF and S. And so we can observe first that each pattern, each steady state, so each model are going to converge to for each steady state, and also we can do that function of delta when delta is increasing. It's also increasing or modifying the transient evolution of these parameters, and the best solution identifies the faster or if you prefer the lower temperature at a single time. Also, if we do the transition patterns in CitcomS, and if we try to over the 2 transient evolution for this parameter, we can observe that this evolution is rigorously the same between the two methods. So there is a really good agreement here between both methods about in terms of transient evolution. So we can now do the same comparison at a higher Rayleigh number. So here it's the same, it's similar figures that I already show you. It's a resolution number of 70,000. So we can first here notice that the amount of perturbation needed to destabilize the cubic steady states is really small. So it's 0.06 for CitcomS, 0.07 for aspect, and 0.75 for other. So really small amount of perturbation, but it's still really close. There is no big variations between the 3 different codes. So we can consider also that there is a good agreement for to localize the transition. And we can also observe that there is still a transition patterns observed for CitcomS. And this is as a new observations. We have also transition patterns for RBF. So I'm just going to a couple of movies to show you how this to evolve. I'm going to restart. Yeah, so you can see that in the first second of the movie, plumes move in one direction, and after a certain period of time, they are going to come back to the initial position, and finally converge to the cubic steady state. If we observe the axisymmetric and steady pattern, we can see the evolution is really similar to the transition pattern we observe at the lower Rayleigh number, but the Rayleigh number is higher, so the 2 small plumes which at the poles at low number are stable and the other plumes on and we can observe similar evolutions for the symmetry patterns here. So these patterns are not steady state, not at steady state. They are now time dependent. So we can, if we compare the transitional patterns between CitcomS and the RBF, we also observe that they don't have the same pattern, same transitional pattern evolutions. I'm going to show you a model that we call pulsating for the RBF method. Yep, moving here. So, the time evolution is really. I mean, the movie is slower than the previous one. You can see at some point plumes are starting to merge. Here only on one side. The plume on the other side didn't merge or even very well separating. And after a certain period of time, these plumes are going to start to pulse very regularly. But the other plumes here on the other side are going to stay at the same position, whatever is the time evolution. So, yeah, it's coming. Yeah, you can see these plumes start to pulse very regularly with time, and the other plumes are going to stay at the same position. So we have a completely different evolution of the transition patterns for RBF as comparison with CitcomS. Results with aspect show that we don't have any transitional pattern which occur for this Rayleigh number. So we have only really sharp transitions. So so now we have some questions about the importance of these patterns and to determine there are if there are or not. So to conclude on the cubic instability, so this figure represents the evolution of the transition, the location of the transition as a function of the amount of the additional perturbation delta and of the Rayleigh number. So the shaded area here, the blue and red shaded area corresponds to the location of the transitional patterns. So at the first approximation, we can observe that the transition is well defined by the two methods, CitcomS and RBF. We did perform the whole model with aspects, so I didn't add here point. We could see with aspect that the points are really close to this transition at 7,000 and 70,000. We can also observe that the amount of perturbation needed to state the cubic steady state. We have a number about 20,000, and also that CitcomS show almost constant thickness for this transition and a very regular transition as a function of Rayleigh number. And for a value of Rayleigh number higher than 50,000, the transition regime broadens, which means that for RBF, the code needs to have higher perturbations of the equal 4 modes. So I'm going now to show you some other results. I'm going to describe the second test cases. So in literature, we can see that the linear stability at higher order of symmetry should be stable, and in particular corresponds to a dodecahedral pattern. So the dodecahedral pattern corresponds to 12 positive anomaly. Here, the initial condition for this pattern is given by these equations with a combination of two spherical harmonics with order 6. So if we perform models so at first at lower number, so here you can see the evolution of the convections in the spherical shell at a number of 10,000 for the two codes CitcomS and RBF, and so you can see the evolution of the convection pattern as a function of time. So even if in the first time both methods are going to converge to a dodecahedral, this structure is not stable with time. It's unsteady. After a period of time, plumes are going to move and start to merge together, and finally converge to a lower order of symmetry. So for the number of 7,000, the dodecahedral pattern is leading us to a cubic steady state. So I'm going to show you how this evolves. So here you can see the dodecahedral patterns, and slowly plumes are going to merge and finally converge to a cubic steady state. And for RBF, so the evolution is different because the final pattern is not cubic, but it's a tetrahedral pattern, and it's also steady state pattern. So here is the evolution. So it's very fast evolution, and so yeah. So we obtained two different patterns of convection. So we can reproduce this this model at various real numbers to see if the dodecahedral pattern is steady at another real number. And this figure shows the final convections so at for the two code for RBF and CitcomS. So RBF corresponds to the figure above the line, and for CitcomS the figure above the line. So we can see that we have a really wide range in pattern as a function of real number. CitcomS is going to have some preferences for even mode. We have an unequal form of cubic pattern, and large models with unequal two mode with axis symmetry patterns. While for the RBF method, we have a more value of mode, because at we have the equal form mode, and at higher number we have equal three modes. So we can notice here, like later about this kind of pattern between the cubic and the tetrahedral pattern. For the number, we have slightly different patterns, which correspond to 5 plumes of 5 convective cells, which is looking like 6 convection for the cubic patterns and 4 convective cells for the tetrahedral. So the two methods are going to show different patterns for the same real number, except for a very few amount of real number 5,000 and 6,000. So we can also compare these results as a function of time. So as you remember for the evolution of the. So I choose to call an excited pattern, and while for the other patterns, do the same. You draw the line between all the plumes. You can draw something like a pyramid. So I call it a Prandtl pattern or the pyramid. So in conclusion, so we compared three different numerical codes with so this code use different discretization methods, and we investigated how each method solve unstable or perturb initial conditions. Thus, for the cube patterns, even all codes model a really good transition. Final patterns of conditions vary with the methods, and in particular around the area. If you remember, CitcomS in particular show unexpected transition patterns at low Rayleigh number. For the dodecahedral patterns, we this is definitively unsteady at all Rayleigh number, and each and this pattern is going to degenerate to a lower order of symmetry, whatever is the mesh through the region, and the final patterns are going to vary as a function of the decision method. And eventually, we presented two new conditions. So these conditions are not this pattern are not unstable, but they were not predicted and could be two new pattern for that we can for future benchmarking comparisons. So this study will stimulate development of benchmark for mantle prediction in 3D spherical shapes. So thank you for your attentions. And so now, if you have any questions.
Thanks, Pierre. If there's any questions, please go ahead and type them in the chat window. I don't see anybody typing while people are thinking, pondering the talk. I want to remind everybody next month's webinar, we'll continue our series on benchmarking. We'll hear from Dr. Eric Hyan and Dr. Hiro Matsui on their efforts in their joint talk, Accuracy and Performance Benchmarks for Geodynamo Simulation. This talk will compare over a dozen dynamo codes that elected to take part in CIG benchmarking exercise. I see a question being typed in.
If we use temperature dependent viscosity, it will depend on the amplitude of the variation of the viscosity. But we could expect, for example, maybe for the dodecahedral pattern, we can expect to have a more steady patterns, and all the plumes could be more stable during the simulation. So we could expect to have maybe a steady state for this kind of patterns. For all the other patterns, in particular for cubic or five-set pattern, I guess these patterns can be also steady at some point with temperature-dependent viscosity.
So, if there are any other questions? If if there are no more questions, I want to thank both Louise and Pierre once again for today's talk. And more information on all of our webinars can be found on our website, geodynamics.org, and this talk will be available on YouTube. Thank you, everybody, and have a good week.